You have fallen into Event Horizon with John Michael Gaudier. In today's episode, John is joined by Doctors Jackie Faherty and Lisa Kaltenegger. Dr. Jackie Faherty received her bachelor's degree in physics from the University of Notre Dame and her PhD in physics from Stony Brook University. Post-PhD, she spent 2 years at the Universidad de Chile on a National Science Foundation International Research Fellowship and 3 years at the Carnegie Institution for Science on a NASA Hubble Fellowship. She is a senior scientist and senior education manager jointly in the Department of Astrophysics and the Department of Education at the American Museum of Natural History. She strives to create more opportunities for underrepresented minorities to enter STEM fields through unique outreach endeavors. Dr. Lisa Kaltenegger is the director of the Carl Sagan Institute, Cornell, and associate professor in astronomy. Her research focuses on exploring new worlds orbiting other stars, especially rocky planets and super-Earths, and their atmospheres in the habitable zone. She is a world-leading expert in modeling potential habitable worlds and their detectable spectral fingerprints, which can be detected with the next generation of telescopes.
Dr. Lisa Kaltenegger and Dr. Jackie Faherty, welcome to the program.
Thanks for having us.
Yeah, thanks.
You both recently released a paper that sort of flips science around in a way. We've always been looking at exoplanet transits with, Kepler and TESS and these other spacecraft. And you guys seem to wonder, who can see us transiting? Now, give me an overview of this paper and how many planets can actually see Earth transiting.
So what we were wondering was if somebody had just our technology, just our, not more. So put a pin in the technology stage that we're having right now, then who could see us like we are looking for other planets, for these exoplanets? And 70% of the planets we found through transits when they block out light from the star by chance when we look the right way. So that was not all of it, though, because both Jackie and me are really interested in the amazing movements of the dynamics of the universe. And so that vantage point where you could see an Earth actually transit the sun, us transit the sun, and then hopefully with big telescopes like the James Webb Telescope, read the atmosphere and figure out if there are biological signatures in it, that vantage point changes. And we were wondering how long you actually had this cosmic front seat.
Yeah, I'll add to that too and say that this wasn't the idea of like the worlds that could see us was not necessarily the novel thing of what we did. Lisa had already had a paper out on that with another astronomer named Josh Pepper in late 2019. Lisa, is that when that one came out? Maybe
that was in 2020, actually, just a little before our paper. And while we were writing it, we were actually starting to get to the point to wonder, I was starting to wonder, is like, how long does this vantage point hold? And then I needed an expert in dynamics. And this is how I basically emailed Jackie and I was like, ooh, I have an idea. Would you like to do this?
Yeah. So the idea that I guess it was 2020, I'm getting my years even wrong, that Lisa had written me, who she was interested in making a cool visual also of the static picture of these stars that are instantaneously and currently at a vantage point right now. And given that the European Space Agency has this observatory that's currently flying at the Lagrange point number 2, about 1 million miles away from us, that is as carefully as one can get, scanning the sky and measuring the positions of stars. Given that catalog has just recently basically provided a revolutionary map of our galaxy, and that's something I'm very passionate about, Lisa came to me and asked about the mapping potential. And what we already knew this right away, that you don't find a planet in an instant. knowing that a star can see you as a transiting planet in a moment isn't what you want to know, because the Earth goes around, it takes 365 days to go around. So even just knowing that they're there for the moment doesn't help you. You want to know how long you are actually staring at a world, how long it's in a vantage point where you could detect it that way. And that's when we started the fun process of using this very, very precise catalog of stars and their motions and playing with time forward and backwards to see how many stars stayed in the position, how many stars were in it in the past, how many stars would be coming in the future, and what those time intervals looked like. So that's really the novel aspect of this paper, is the time frame of it all.
Just to toss this out there, that was the Gaia spacecraft, right?
Yeah, the Gaia Observatory. It's also a spacecraft, so all of it gets said together.
What to me is so fascinating that we got to the point with the Gaia mission, with the Gaia spacecraft, that we can actually now take the dynamics of our cosmos into account, of our galaxy, of our stars' motion, of the neighboring stars. And so this sliver, this really just a sliver on the sky, to see the Earth's transit or to see the Earth's block light from the sun, you have to basically be in the plane of the Earth's orbit around the sun, the ecliptic. And so you can just extend that further out, and you can be just a little bit above and a little bit below it, so that you can still see the Earth as a transiting planet and not look just a little too high and miss the transit of the Earth's star at the sun. And so what's just so fascinating to me is that even so, we only live for hopefully like about 100 years, but you could now do that dial. You could turn that dial back. You can turn it back thousands of years and thousands of years into the future. And so all of a sudden you actually get an idea, or you get the answer to how long is such a vantage point even valid. You know, is it 10 years? Is it 100 years? Is it 1,000 years? And to me, one of the things that this work definitely did is like it makes all the planets that we found through those transiting methods much more precious. I appreciate them much more because it's a moment in time where we get to see them too. Because let's say 10,000 years from now, we probably wouldn't be able to see them anymore. And this is where this time component comes in that I find so fascinating. It's not I see you, you see me. It's really, we have to be at the right vantage point to see other transiting planets. But these systems, if anybody is to be looking on these systems at us, even with our technology only, have to be at the right point in space too. And that point, as Jackie said, changes. And to be able to actually take the dynamic of the universe into account. And Jackie and her team made amazing visuals for that. I think it's just great because, you know, this planet saw us, you know, a couple of the stars of planets we already know exist, some exoplanets, there's 7 exoplanet hosts in our list. And you're like, so Ross 128b, if there were anybody looking, they could have seen the Earth 3,000 years ago transit the sun, but they lost the vantage point about 900 years ago. And so this question about if you could have even deduced that there was intelligent life on our planet, you know, you could have figured out that there's life if they just had our technology, but it's so interesting. Would they still be looking? Would they now see radio coming if there's a day on that planet and say, no, look, so they name a technological civilization? I think it's just a fun play to think about it.
Now, timescales. So is there an average with everything moving around and proper motion of stars and all these things just conspiring to move the universe around? Is there an average time that an exoplanet could see Earth transiting? I mean, how long of a window is it for most exoplanets nearby to actually see this? Is it a matter of millions of years, thousands of years?
Well, I actually think to answer that's not a question to answer without this extra thing, which is you need to know how far away the star is. And that is what became like a novel, intriguing, should have been intuitive, but it missed me a little bit at the beginning of when we started working on this aspect of this. And that is because the closer you are to another star, the more its motion in the galaxy is detectable by you. So the closest stars have the highest proper motions, which means we zip by each other very quickly. And that also means that they will be zipped in and out of that perfect spectator view seating fastest. And so one of the things that we found when we looked, and by the way, in this paper, we looked at a plus or minus 5,000 year change in time from the date that the Gaia telescope, the date that the EDR3, the Gaia's early data release 3 catalog came out, which is 2016. And so because of that, the epoch of that catalog, it's 2020. So you go back 5,000 years or you go forward 5,000 years. And when you look at that time frame, you find that if you limit yourself to just the stars that are at 30 parsecs or like 90 light years, the amount of time that they spend on average is about 3,000 years for any one of those stars that are in that volume. If you expand that to the larger volume that we looked at, which was 100 parsecs or 300 light years, it's double. So what you're seeing is the farther away that you get, the longer the period of time is that you could remain at a vantage point. But the thing that you lose is the distance. And so one of the awesome things I think that I took away from this too is that the closest stars, which are the ones that we all get so excited about because they feel like family members to a certain extent, it's our solar neighborhood, it's the ones that we like live on the block with, that those are in and out so fast that maybe if we start staring at the nearby sample and we're like, oh man, no transiting planets there, hopefully astronomers are around doing this work for the next 500, 1,000 years, whatever, check again, because there are planets that are within, that we found had a transit zone that were in and out of a zone in just a few hundred years. And so near things, while they are prime targets for us to consider for like interstellar conversations, they're the brightest examples of their own classes of stars. They're usually the best studied. They have the highest relative motion with us so that we can really tell where they're going, which means they're in and out the fastest.
There's something ominous here. Before we move on, there's something ominous about this. Earth has broadcast a biosignature, our oxygen and methane, that could conceivably be seen, and an alien civilization says there's probably a biosphere there, and it's done it for several billion years. So a huge portion of this galaxy has been able to see us transit at one point or another, right?
Well, if you go with how long could somebody say that there's actually life on this planet, yeah, you have the 1 to 2 billion year time frame where oxygen built up in our atmosphere and the biosphere completely changed the air on our planet. And so, yeah, anybody who would have looked curiously, like with our level of technology, that's basically what we wanted to put. So a James Webb Space Telescope that could find, or they could probe the air of small transiting rocky planets in the habitable zone that could have seen us. And so the question in a way is, and I think this is where you're going with, is so what I usually get as the next question is, so does it mean there's nobody out there? And sometimes I like to just wonder about this a little bit more, right? Because really the inherent assumption of this conclusion is that everybody would want to talk to us, that everybody would want to come and visit us. And I love the Earth. It's my favorite planet. The people on it are my favorite people, like not even a question. But if you would assume, and that's a complete hypothetical, right? Let's assume the universe is actually teeming with life. Then why would we be the place to visit or the place to call? Because we just got astronauts to the moon. We haven't even gotten people to the next planets yet. And so maybe we're just not that interesting yet.
But isn't that sort of a sad solution of the Fermi paradox? Because that could lead to a situation in the galaxy where everyone just silently watches each other. Do you think about things like that solutions to the Fermi paradox that could be drawn from studying exoplanet transits?
I just really think that you're saying that everybody's watching each other. Why? If other people or if their life is, again, completely hypothetical, but if life were common in the universe, then at a certain stage, maybe it's interesting enough to talk to everyone else, right? We want to talk to advanced civilizations. We don't want to talk to a place that hasn't figured out how to go to the next planet yet, right? We actually assume that whenever there's going to be a contact in any movie, in any scenario that we envision, that it's going to be with an advanced alien civilization. I just kind of would point out or think that maybe, and I hope that is true, we are at the point where we can now find life in the universe with telescopes like the James Webb Space Telescope coming online end of this year. And then in 2027, the extremely large telescopes, by looking at the air of transiting planets that are in the habitable zone and rocky, and finding this combination that you talked about of oxygen and methane on a temperate planet that we cannot explain with anything else but life for the oxygen part. So we might just be on that threshold. So I would say it's actually much, much more optimistic in my point of view. If we just made it to the threshold, then who knows what good things are coming.
I would also point out too that I usually think about life in the universe in layers, and I think of it as the nearby stuff and the farther away stuff. And that maybe part of what if I were to find a planet that had life on it that was across the galaxy at like several kiloparsecs away, I would have a very different vantage. I would think about it very differently than if I saw like one at 4 light years away. Like I just want to do a population study, like visiting, sending a signal, all of that. It's like I see it as like double sci-fi. Like it is sci-fi to think like, okay, we find life around Proxima Centauri, we can travel back and forth. Like it doesn't seem so bizarre. Even to say like the 30 parsec sample or the 100 light year sample, that still feels close. But what you said at the beginning there was like, okay, so there's stars across the galaxies that have seen us, but it's like totally different when you're talking about the other side of the galaxy. Now maybe I have to go super sci-fi in my head and think about civilizations that are so completely different, but then I'm not doing a good translation. I'm not really trying to understand because I don't even know what that would look like. If you could look across the entire galaxy, pinpoint the Earth, wouldn't you focus on what's near you? And that's one of the things that I learned a lot about in doing this study was the focus on the nearby sample. There's that extra parameter of chance moments because you don't know when you're set up correctly to be at the point where you could detect each other and find each other. Now, sure, you could be like some super advanced civilization, but who's to say that Ross 128 or Wolf 359 or any of these other worlds or TRAPPIST-1, for instance, TRAPPIST-1, the famous exoplanet system, 7 rocky planets around an object that's barely a star, that those 7 rocky worlds, like we found them, but it's about 1600 years before they can find us through the same method. And what will life look like on this planet at that time? Like I use that as my perspective narrative on this. And I felt very much like chance moments probably drive a new aspect of our attempt to understand like how and when or if we could communicate and find each other across the galaxy. I think of things on the other side of the galaxy or in a different galaxy even as very, very different than I do our solar neighborhood.
What you were talking about now, sorry, what were you talking about before? Light needs time to travel. So that means if something is 100 years away from us, 100 light years away from us, then it sees the Earth right now everywhere 100 years ago. But if something is, 100,000 light years away from us on the other side of the galaxy, well, a bit less, 80,000 light years away from us, then it sees the Earth as it was 80,000 years ago. What was probably quite interesting, but again, I'm asking is like, let's say you have super duper telescopes, you can figure out what's happening on the Earth. Who would you want to contact? Who would you want to talk to and why?
Right. It's such a good point too of like, maybe it becomes true that there are very rapid phases that species go through that we don't fully understand because we've only ever studied ourselves. And that, maybe advanced civilizations know. So everything that's really populated with in really advanced life right now is on the other side of the galaxy, and they see us, they might be like, no way, man, 80,000 years, 80, say it's the other side of the galaxy, or even 50,000 light years away. They're like, forget it. They're rapidly running through that phase. We have no idea what will be going on there or what it's really like there. The nearby sample is where it's at. Like, that's where I feel like I learned the most about where we might be thinking in terms of civilizations detecting each other. And this paper made me feel both better and worse about the idea of finding life in the cosmos for us.
We are in a very strange position, given that we are a radio producing technological civilization, but we've only done that for about 100 years. And if you're looking at the local group of nearby stars and exoplanets, there may not have been enough time for them, even if they know about Earth, and then they suddenly saw us light up in radio, and they see our radar and whatever else they might see at that distance, say it's 80 light years out. There's not been enough time yet for them to send a message to us. So they receive it and they're like, well, we're going to send it back. So that's 160 years. That's longer than we've had in our ability to monitor radio and create radio. So we could be in a situation where someday in the coming decades, all of a sudden the sky lights up with radio messages from nearby stars. And we may well be surrounded by civilizations. We just don't know about it because there hasn't been enough time. So do you think that's actually viable? I mean, do you think that the reason that we see the great silence in SETI is simply because there hasn't been enough time for anybody to really know we were here?
Let me maybe ask another question on this. So I'm thinking about this a little bit, especially since we did this paper. There's a question that comes up a lot. It's like, so does it mean there's nobody out there? And I've already given you the one answer that is like, why would you contact us if you had options? Right? Again, with Earth being my favorite planet. But also think about these 100 years of radio that we had so far. We're going away from actually wasting radio signals, right? The biggest signals were initially when we didn't know how to control radio signals too much, like in this first half period. And then you might be talking about targeted systems. But now, if we're going away from radio observation, I'm just thinking sometimes, and this is again completely hypothetical, let's assume we're going to the next technology step and then another one and then another one. We're doing internet, we're doing Bluetooth, right? All of these different things, and we don't know what's going to come next. But now, if there's something that's going to come next, you could also argue there are actually messages that are already lighting up our sky. We just can't decipher them yet. We can't see them yet. We don't have the technology yet. And maybe that's the next step where we'd have to be. And then some people are saying, well, but they would know that we can only do radio. And you were saying they would find us through radio, right? I think, let's assume, and this is a hypothetical, let's assume radio were an outdated kind of way to look for other civilizations or do something else, then you would have to have a very nice NASA or something else that would allow you to actually keep a big, costly radio telescope open just for a chance that somebody's going to radio you like another less advanced civilization or back. So there are so many answers to this. Why is there silence, right? And I think a lot of them are always, again, embedded in that we assume if anybody were to find us, they would immediately want to talk to us or want to come visit. That's kind of an interesting assumption, isn't it?
It is. Now, let me ask you this. You found within the local area, I think it was over 1,700 star systems that could TESS transit. Did you find any that had interesting Earth-like exoplanets that were known to be around them? So is there any candidates there that could have a civilization on it?
Oh, absolutely. This is where so one of the things is we only have 7 in our list, but of those 7, 3 actually have a couple of planets. Turns out in total it's 7 planets in the habitable zone that from their size or mass estimates should be rocks. And that's actually an incredibly low number. And the incredibly low number is because we usually haven't looked in the ecliptic, because it's crowded with stars. And so it's just a little bit harder to find a transit signal if there's a crowded field of stars. So we expect actually hundreds of planets within the habitable zone that are small enough through the transit signals to be rocky, to be in that sample. We just don't have them yet. And it is because the region is crowded. But now with our list, so the list of the 2,043 stars that Jackie and I made, I think there's enough people who are now interested in stars that could see us transit as well, that they became priority targets for some of those searches. And among them is the TESS search, NASA's Transiting Extrasolar Survey Satellite. And I'm part of the science team. And so we are looking, or TESS is looking currently at the ecliptic in the extended mission, because we didn't have it in the main mission in the first 2 years, because it's just a little bit more tricky to get transiting signals in a crowded field. But now we do. And so hopefully we will find many, many more of these planets within the habitable zone that are small, so that should be rocks, so somewhere between 1.9 and 1.6 Earth radii. Below that, we only know of rocky planets that transit. The other ones could start to have more gas. But basically, we're expecting hundreds of those to come in the next couple of years, because TESS is looking right now, and a couple of ground-based surveys are too. But we have a couple of really great systems already. And Jackie mentioned one, TRAPPIST-1, with the 7 rocky planets, and 4 of them actually within the habitable zone. And they will, or if there's a day there, if there's a civilization there, they would see us in the future. But Ross 128b, there's one roughly Earth mass planet within the habitable zone of that star. They would have seen us already. And there's Teegarden star that will see us, or will start to be at the right vantage points in 29 years. So there are super interesting close by targets already. And we hope to get a lot more.
Yeah, I want to add on this too. So this question of like, okay, so how many of them had planets around them? It as if we've looked at every star in the sky for the planets yet. It's really important to realize that searching for planets is not, it's like this interesting game of what the best targets are. Like, where do you focus your energy to try and find planets around their stars? The nice thing about TESS that Lisa just mentioned is that it is all sky. And so it is looking in all directions. The satellite, the observatory before it, Kepler, was at a very, very narrow, small portion of the sky. And the stars that we found are in the projected ecliptic along a very narrow range of the sky, but all over the sky in the north and the south. And what's also intriguing, if you look at our table and just look at the star names, you'll see some of them are what I call famous stars. Like the closest is Wolf 359. This was a star that was a character or a location in a Star Trek Next Generation episode. There's a whole audio podcast on that star. Teegarden star is in there. Wolf 28. There's famous catalog names in there. And then there's stars whose names you haven't heard of because no one was even looking at them before. There's stars that are really discoveries amplified by the Gaia survey. They're stars that we know almost nothing about, except now we know that they're stars that are in this critical area of the sky for the reverse vantage point, and they're very close by. And so this is an excellent sample of 2,034 stars in the past, the present, and the future that have this vantage point over a 10,000 year period. And so it's important to realize that, astronomers need that extra motivation sometimes to target some of the stars. Nearby stars are easy ones to want to target, but we went out to a volume that isn't necessarily just nearby stars, like it's all the way out to 100 parsecs, so 300 light years away. And so within that, there are stars that are like 35 light years away, 45 light years away, that no one was paying attention to. And now we've got great motivation to study them and to find out more about them and to look for their planets.
And I think what's great, what Jackie was saying before, is just like now we also know that these vantage points, even so we kind of should have known, right? But it was never really clear that these vantage points can get lost and gained really fast. So even so you haven't seen the planet transit, it's actually worth looking back at this sample or, at the close by stars and look again, because that could change. And maybe all of a sudden you actually do see something transit. And by the same token, some of the transiting planets that we've already found, we will lose.
Yeah, exactly. You're not going to hold on to that forever. So keep that in mind as this extra parameter. To me, thinking about this was like learning a new dimension to our search for life in the universe. It's the nearby star samples of a vantage point from you is critical.
So let's take this from an alien perspective. So we often make the assumption that if an alien civilization is going to be detectable technologically, they must have math and science. You must have math and science to build a radio transmitter. So say we're at Wolf 359 and we've managed to get rid of all the Borg cubes and destroyed starships, and we see Earth transiting. As scientists, and imagine yourselves as alien scientists, as scientists, what is the first step past seeing a transit in determining if there is something interesting about the habitable zone world in this solar system?
So what we are planning to do in that case is actually to first look at the atmosphere of such a planet and try to figure out if there are biosignatures. And that will be the combination of oxygen and methane in the atmosphere of such a planet. And then hopefully we'll build a telescope just to look at that one planet and learn more, whether or not there are changes in the surface that could tell you that there's some biota or some sandstorms or anything going on at the planet. So do real good recon, try to learn what we can. And there is an ongoing discussion in a different community, the ones who are actually searching for extraterrestrial intelligence, or the SETI community, about whether or not at that point in time you should send a message. They would listen for sure passively, but whether or not to send a message there is another question that also everybody should get involved in who's interested in whether or not to do that. However, bringing back to the point that you had early on, you could tell that there's life on the Earth since about 2 billion years ago. So in a way, if you're trying to hide life, the cat's out of the bag.
Yeah, I'll add to this too and say that the reverse alien astronomer perspective, once they had detected that we were a transiting world, would probably begin to, like we do, focus harder on that one star with the world around it that they had detected, so that you could then figure out that it was a solar system, that you had more than one world there. You would make an attempt to directly image the planet. And so we've been talking about the transiting method. The method that I work on the hardest is the direct imaging method. And that at our current stage of technology is limited to studying the youngest stars because they're the hottest, and to the biggest, youngest star planets. And that's because big ones are hotter and we can actually resolve and get their contrast out after we block the light of the star. But what we do once we start focusing in on the direct imaging is we look for weather patterns. And that's, you monitor that planet very, very carefully. You look to see what its inclination is. How is it inclined to the rest of the objects that are orbiting the star? I think what you would find is that they would, I mean, it's funny. It's like makes you feel a little uncomfortable. You become like a point of light data specimen. We're like a little lab rat for somebody to study. And we're doing that for other worlds outside of our own. We'd like to know everything we can about them from a distance, from afar. Like Lisa says, sending a probe is like really extreme. It's first, you focus a huge amount of energy and attention to know everything you can about the potential of that world before you would do anything at all. At least that's the human perspective right now and how we're tackling the problem.
Doctors, I'm going to ask you both this question, and it's something that I think about, but it doesn't really mean much, but it's something because there's nothing we could do about it. But does it seem eerie to you that this planet could be watched? very, very possible, well within science, that this planet could be watched, and for the entire existence of humanity may have been watched.
I would say yes to this. And Lisa, I don't remember how much we might have talked about this as we were, Lisa and I would have multiple conversations as we were kind of looking through the catalog and like figuring out how long the stars were there, and then looking through the list. And as somebody that studies the solar neighborhood at length, I'm very familiar with the names of many of these stars. And it was almost like I started to get that feeling like somebody I knew was watching me from the window, because these are stars that I know so well, but then all of a sudden to think they can do what we're doing back, it was like opening the perspective window on how it really works. That just like a civilization here looks out, they can look back at you. At the flip side of that, I also felt like it's not that many. It didn't seem that bad. We started with a sample. The sample that we did this study with is called the Gaia Catalog of Nearby Stars, and it consists of just over 300,000 stars. And among that list of just over 300,000 stars, it's just 2,034 of them that land in that spectator seating vantage point. So it was both a lot and it wasn't that much, but the ones that are in it, they're famous. They're ones that we've paid a lot of attention to over the years. So I think it's a mixed feeling thing.
I have to say, for me, it's a little bit, to me, the sky just became a lot friendlier when I actually put this all into perspective. And I just, we do not know, of course, but I choose to believe that if there's life out there are some people rooting for us. And the idea that I have there is, they saw the oxygen rise in the atmosphere 2 billion years ago. And then if there's a there out there, and then they're like, oh my God, now this planet is actually developing in a biosphere. And then again, it depends a little bit, but let's say even closer, the ozone hole that we created. I kind of hope somebody's rooting for us if there's life out there saying, oh my God, they're destroying the ozone hole. Okay, they made it. They figured it out. They are fixing it. And oh my God, they're doing climate change. Come on, people, get it together. Not people, but come on, get it together, Earth. And so to me, I just choose to believe that if there's somebody out there who's found us, that they're rooting for us, and we're like, come on, everybody go through this. You can do this. Figure this out. Save your planet. Stay there.
So
we want to talk to you in the future.
We could be a case study, a textbook somewhere out in the galaxy in some alien university. Earth is a textbook on what happens to a planet that has a civilization on it in its early stages, and that's what everybody knows about us. We're that planet, the one with the people.
I've had this conversation with friends before on the other astronomers, where I've had its thought at one point. I was like, you know what? I bet there's like a PhD student, alien PhD student, whose job it is to like, they already know that this like teeming with life, planets are all teeming with life, and they know how many of them have like intelligent civilizations. Nobody cares enough to visit, like Lisa's saying, like, why would you? But they are interested in like how many of them break through the like atomic bomb crisis when you realize that thing can happen, or how many of them blow themselves up. Okay, so you make it through that. Now, how many will make it through the phase where climate change occurs? How many of them make it through when you have billionaires rocketing into space and they end up rocketing out so much that they change something for the planet? Like, I loved the idea that it becomes almost boring to study one, and that you do a population analysis, and that we are a case example within that, and that each one of the phases that we're passing through is one where, an alien civilization watching is just to see what stage we get to. And that's kind of cool. But I mean, Lisa's being super positive there with this whole, like, you liked the idea that they're rooting for us. I thought more like neutral. Like, I bet they're like, well, too bad. They made it to this phase. I don't think that they're going to make it past the next one, because they're not doing so good when it comes to their, I don't know, global political structures, and somehow they figure that out by like seeing light pollution somehow across the planet.
I was about to say, I love your idea of the PhD student who's like, come on, you're my PhD project. You have to make it. Come on, you cannot go down that road. What I'm going to write on.
Right, exactly.
It puts a new meaning to the words Earth Sciences.
Absolutely. I think we should redefine that.
Yes, redefine it. Now, it can actually get much, much worse because you could have a civilization out there looking at us saying, that's a really nice exoplanet they have, and they're going to cause their own extinction. So we'll just bide our time and eventually go and take it over.
This is the really interesting thing where what we haven't talked about yet is, when you're searching for life, you're not just searching for you and me. And it is actually incredibly hard to kill life on our planet. You would have to sterilize the planet all the way a couple of kilometers down. And that's actually really hard to do. But killing you and me and us killing ourselves is easy.
Well, it's also worth noting, too, that if one worries about alien civilizations and sterilizing Earth, that would be really hard. But there is one thing that can do it, and eventually will. As the sun's luminosity increases, it will sterilize this world. So that's what we really should be scared. Now, it seems to me that one thing that our civilization does produce that is being advanced as a biosignature are things like CFCs in the atmosphere, and that such an artificial chemical can be seen at a distance. Now, if we look out at these exoplanets that are transiting, and we start to characterize them with the James Webb Space Telescope, and we start seeing strange things above and beyond a biosignature. I mean, a biosignature would be amazing. We would puzzle over it and argue about what these weird oxygen levels and methane levels mean. And of course, some people are going to say, well, it's nature could produce that. So some things like that. But there are unambiguous signals that we could see. Now, that would be close by, say it's 25 light years. Does that strike you as almost too close for comfort?
I think the first point that I would mention is that luckily the CFCs that you were mentioning are actually incredibly small amount of the atmosphere. So the features are incredibly small. And so you'd need something much bigger than the James Webb Space Telescope to find them. But let's assume we'll have something like that. I think what you were talking about, the oxygen and methane levels, I am pretty much predicting that if we could find CFCs on other planets, that somebody will come up with a method to make it with a different geology, because this is the way of science, and it should be. You throw all your skepticism on it, and then you say, like, well, if the geology is this and this, maybe we could come up with freons in the atmosphere and so on and so forth. But that's a good thing, because that means we'd learn more. But I think what it would definitely do is have us invest in a bigger telescope to learn more about that planet. And 25 light years, now you're talking about being able to maybe send a message and get one back within a lifetime. What's pretty cool.
Yeah, I think some definitive signals that, we've got something is if we send a message and we get a return answer. That's a pretty interesting, and frankly, I think it's scary and it's a compelling aspect, because as much as, like Lisa says, we can search for our biosignatures, but at some level there might be always ambiguity as to how we might interpret that, chemical signature in the atmosphere as the telltale sign that life is there, life is on that world. But something that would not be served with much ambiguity is for us to send a clearly radio message of sorts from here and get a response of sorts, a la Carl Sagan's Contact, and how we got a return conversation. And that is, an intriguing aspect of what SETI might be looking for and what SETI could do. Not to say that might happen in our lifetimes, but I would be very hopeful, scared, but hopeful that kind of thing might be a signature that we receive.
I think one of the things that's really interesting in this question, in this messaging, right, as Jackie was saying, probably, you want to have the message encoded hopefully in English or another language of the world that actually says hi back. And then people will be like, oh, okay, that is a message. But if you look at the evolution and what they would require in a way to get to another us with radio telescopes, maybe it doesn't need to be us, but to another civilization with radio that wants to communicate, that is looking, I think even though we know that 1 out of 5 stars has a planet within the habitable zone that's small enough to be a rock like the Earth, once you start to actually put further constraints on that the evolution has to get to a radio civilization, I think it stands to reckon that you actually bring the number very far down. And then maybe, especially at that stage where you're still in the radio phase, there might be only places far removed and in between. And then time becomes a problem. When can somebody see a signal, and do you still have a receiver to receive a radio signal back? But it's a fascinating question, and it's a great part of the search for life. I just think it's a completely different question you're asking. So are you trying to find out how an Earth-like planet works through its evolution, how often life evolves, what kind of life could evolve? Are you interested in, single cells organisms and multi-cell organisms, or anything, whether it be dinosaurs or whales or anything else? Or do you want to find a civilization that you can communicate with? And I think these two parts are parts of the same story, but one is more like a needle in a haystack, while the other one hopefully is the haystack.
Now, let me ask you this. You mentioned the radio window, where we don't really know how much longer we're actually going to produce very powerful radio signals. What about the transit window and something like an Arnold louver, where you have an object that creates a strange feature in optical transits, then using that as a way to announce your presence more long term? So in other words, is looking at weird transits something that civilizations are more likely to do very long term?
So I think this is a fascinating question. And in the SETI searches, I think this one is intriguing. And I think you've had David Kipping on, right? You've had
yes, many times.
Okay. And, these are the kinds of things David Kipping throws out there. I like or discusses in lots of detail. And I think that from my perspective, astrophysics research that takes on these intriguing different concepts of how we might find a civilization, or how another civilization might attempt to make itself known, are all important for our minds to stay very, very wide open to. And I don't think, though, that we can answer at all whether that would be the way, that would be the path that another civilization would think, this is how we'll get their attention. Do you know what I mean? That's also asking us to once again put on our opinion hats based on how we do things or how we think the world is going, and make that decision. Because frankly, I don't know that you can answer this one way or the other. I do think that it's an intriguing, fascinating idea, and one that we should pay attention to. I will say Lisa has come up with some really cool ideas too, to look for intriguing signatures of life that might exist on other worlds that I thought were really outside of the box. Lisa, I remember you were giving a talk once, and you were talking about the life that might exist around M dwarfs, which have crazy flares that go off, which is not good for us, but it might be great for bioluminescence life that might exist in some sort of feature on a world orbiting an M dwarf. And that maybe what you do is you look for signatures of bioluminescence that might exist. And so from that perspective, I think these different avenues that aren't as obvious of somebody announcing, hi, how are you? My name is Ross 128b Planet Civilization. Who are you guys? Instead, these other methods are really important for us to continue to think outside the box and figure out how they might communicate. But I don't think we can say what the way they will communicate is.
I think also taking, the recent private launches into space into account and so on, I agree that it's kind of an interesting idea that somebody could put this out to call our attention. I think if our thinking is common, and again, we don't know that, then it's probably something that they put out in space as art or as decoration or as advertisement. It just looks weird to us, but it might not be, to actually announce their presence, because there might be better ways to do that. But we might just stumble across something that an advanced civilization just put up there, like a space station that has a weird big shape. I don't know. But I think, as Jackie was saying, it's good to keep an open mind. It is very, very hard, and I think that's the hardest thing, to not just superimpose what we believe on all of this, of what our importances are. And this is where, again, this thing comes in that we're saying, oh, the big silence, it means there's nobody out there. Well, it just means there's nobody out there who wants to talk to us, you know? So it's kind of interesting sometimes to stop and to think this through and say, like, what am I actually assuming? And some of the assumption that say that everybody's doomed is that if somebody were out there, they would always be here and wanting to talk to us. And so I think it's good to sometimes question why your answer is a quick, everybody's dead, or it would be like all signals are away.
That would be amazing to see a transit of something so weird that we think it's alien artwork, and that they're simply sending a message that art is universal instead of science is universal. That's an interesting perspective.
See, we're writing a new paper right now.
My last question for you is, what is the future like? Are we going to be visible to how many worlds in, say, the next 10,000 years or some number like that? So how often does this sort of cycle in the future, our visibility to the rest of the Milky Way, or at least the local area of the Milky Way?
Well, I'll give you a take on this, which I think is important. And that is keeping in mind the volume sampled that you're talking about, because the volume sampled is very critical. If you want to know about our nearby solar neighborhood, then that is going to remain a fairly small number because of the various things that I said at the beginning that we were discovering. You know, the motion is going to take them in and out fairly quickly. And so, but it depends on where you want to cap your volume. And the thing that I'll say, Gaia has provided us with an unprecedented insight into the motions and positions of stars across the galaxy. That said, it's really only provided us with about a percent or so of the stars in the galaxy. So how many are coming in and going? I would still want to keep you at a local volume. I would still want to have you look at the nearby stars. But say in the future Gaia releases, we'll be able to do an even better, unprecedented look at stars that are much farther away, because the precision on both their distances and their motions are only improving as the future data releases are coming over the next 3 years. So we will know more. And the other thing that Lisa and I have been talking about is that with the increased precision that Gaia is giving us, plus the one thing that we did not use in our analysis is the radial velocity component of the motion that takes things towards or away from us. So we kind of capped our volume. But Gaia is releasing a radial velocity catalog in the next year, which is going to take us from just about 8 million radial velocities that we got from the Data Release 2 catalog to over 30 million. And that will also increase in the future data releases. And with that, we will be able to look at the time variable catalog over a much larger span of time, because we'll be able to take us from looking at kind of this projected just proper motion view, linear view, which is conservatively capped and well done at plus or minus 5,000 years. But we will be able to take it towards more than 1 million years. We'll be able to look 1 million years in the future and 1 million years in the past, and maybe even farther, a couple million years in the future and in the past. And that will all be enabled by future Gaia data releases, which are all coming in the next year or two.
So if you go with what we had in this paper, what we have, the roughly 300 light years, then within the next 5,000 years, 319 stars will gain that vantage point to find us. And I think within the last 5,000 years, about 417 stars lost that vantage point. So you see, like in about 5,000 years, the turnover rate within about 300 light years is roughly 300 to 400 stars. So that means also for us that we should find more transiting planet. What's really interesting, and as Jackie was just saying, what would be really cool is if we could extend it out. And that was a question you had before, So does that mean how many stars have seen us since this 2 billion years ago, when oxygen and methane actually indicate the biosphere on the Earth? And so we won't be able to go to 2 billion years, even with the best measurements of the Gaia catalog. But as Jackie was saying, we can go a couple of million years. And so it becomes even more interesting to see what's really the average way of the average time somebody has to see another planet transit, or in this case, the Earth transit the Sun, but also some of these stars that could have seen Earth's transit and found a biosphere, let's say 1 million years ago, are now quite outside of this ecliptic, of the sliver, because of the time component. And so it's going to be really interesting because they're going to start to be sprinkled all over the sky if you can go back in time further. And so I'm really looking forward to what we're going to find with the next steps in this exploration, where we go deeper into.
Yeah, and if I could give you one other thing to look forward to, and that is, we were talking about the solar neighborhood and the stars that are nearby. But a very important idea or a very important fact about the solar neighborhood is that it is an ever-changing thing, that stars are moving towards and away from each other, and that flybys are actually a major component of the solar neighborhood. So for instance, we've only recently discovered that 70,000 years ago, a star called Schultz's star flew within about 60,000 AU of our sun, which is well within the Oort cloud. And if you want to look forward to something, in just over 1 million years, there's a star called Gliese 710. It's a K-dwarf, and it will fly within, at its closest approach, which has an error bar associated with it, but 16,000 AU of our sun, which means it will be well within our solar system. It's probably carrying with it its own Oort cloud, Kuiper belt, solar system. And that kind of close separation means, like we've been talking about the transit method, but that's a planetary system that might be headed right for us, and we're headed right for it. So solar neighborhood, ever-changing area. And we only know about these flybys because of the precision of a catalog like Gaia. We knew about Gliese 710 and Hipparcos, but our refinement of understanding how close a star like Gliese 710 was going to get to us was enabled by Gaia. And we're going to have more in the coming years because we need radial velocities in order to really say who's coming and going. And the most dominant star in the solar neighborhood is the M-type star, or the lowest mass stars, the M dwarfs. And those we haven't been able to get radial velocities for them in bulk, but we're going to get a lot of them with Gaia. So we'll be able to say even more about a flyby rate, given we'll be able to involve the most popular kind of star that exists in the galaxy.
If we make it for the next 1 million year, and I think we now have a really good incentive to, we might not have to travel that far to the next star.
Right. It's coming here. We're going there. So I keep saying we really need to, everybody wants to focus on Alpha Centauri, Proxima Centauri, and this flyby. Gliese 710 is doing its own thing to get to us.
Well, and if it's a Type K star, those are a pretty attractive star to settle.
Absolutely. Yeah. Yes.
Well, thank you both for joining us today. And I hope as your work continues and the Gaia data comes down, you'll come back and give us an update.
Absolutely.
Great.
Thanks for listening. I am futurist and science fiction author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author John Michael Gauthier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing. And be sure.
And that's enough of that.
YouTuber forever. Like, subscribe, and hit the bell.
Sell out.
What?